So we've previously talked about, at some depth, the Lewis model. The Lewis model is an oversimplification. It's a lot simpler than it actually is. There are more advanced bonding theories that apply quantum mechanics to molecules. We didn't really do very much of that. And modern quantitative approaches, where they actually use numbers, can accurately predict a lot of the properties of molecules, including bond length and strength. You can predict molecular geometries. You can predict dipole moments. So the amount of electronegative force difference basically across a bond or across a molecule, you can calculate and predict those things, and people do that. That's well beyond the scope of this class. That's like a couple years past this class at least. And so we're going to look at some of these theories in a qualitative manner. So not looking at the hard numbers necessarily, but more thinking about trends and things that are weak and things that are strong and things that are bonding, things that are not bonding. So not as much numbers, more just qualities and trends. So electrons reside in quantum mechanical orbitals. These are localized on individual atoms. So these are our s, p, d, and f orbitals. If you remember back to our some of our quantum stuff. Remember, our s block is all the way on the far left. That's our first two columns. Our p block is the far right 6 columns. Our d block is the middle rectangular section. That's all our transition metals. And then the f block usually gets pulled out and set below the periodic table. These atomic orbitals can be hybridized that blend 2 or more standard atomic orbitals, and we're going to look at that. So when 2 atoms approach each other, if you've got 2 atoms that are coming in to potentially bond or interact, as they near each other, the negatively charged electrons, the positively charged nucleus are going to interact with each other. And depending on how they interact with each other, they either will form a bond or they won't form a bond. So valence bond theory, we're going to be looking at energy changes resulting from those interactions. And in general, a chemical bond is going to form if the system's energy, that molecule, those atoms' energies, is lowered, if they're stabilized by that interaction. And just as a reminder, breaking bonds requires energy, forming bonds releases energy. Because you're in a lower energy state when you're in a bond, and so to get you out of that, you have to put energy in to break that bond, to reduce that stabilization. So forming bonds releases energy. Because it is stabilizing. It lowers the energy of the atoms of the system. So if we look at an interaction between 2 hydrogen atoms, the energy of 2 hydrogen atoms is going to be at its lowest when they're separated by a distance that allows their orbitals to overlap. So we've got the 2 dots here, the black dots here being the nuclei of our 2 hydrogen atoms, and then the blue spheres being our 1s orbital. So that's the spherical, in 3 dimensions, orbital that our hydrogen atoms have. And we've got over here on the right, very spread out. We don't have very good overlap between those orbitals, those 1s orbitals. Over here on the left side, we've got too much overlap. The nuclei are too close together, and so the nuclei probably repelling each other. The overlap was a little bit wonky. And in our point 3 here, this is our lowest energy state because we've got this really good overlap, that sort of that Venn diagram, the shared space. Good orbital overlap. And so that is about where our hydrogen atoms are going to settle at, because that's the lowest energy state. So they're going to spend most of their time in there. They're probably going to be doing a little bit of bouncing away from each other, so they'll kind of shift to the left, shift to the right. It'll slightly increase their energy and change the bond length a little bit, but for the most part, we would expect to find them at this bond length. Our interaction energy is usually negative, stabilizing, bond forming, when the interacting orbitals contain 2 electrons that can spin pair. Oftentimes this is going to come from 2 half-filled orbitals. So if we look at hydrogen, if we've got 2 hydrogens coming together, they've got half-filled orbitals. Those can go together and they'll spin pair, one up, one down. And this matching that's the bond that forms. It's a spin paired combination of 2 half-filled orbitals. We can also get, it's also possible for 2 electrons to come from a filled orbital and have that overlap with an empty orbital. So one atom provides both electrons. And the other one's just kind of there. Question?
So the interaction energy is kind of like the change, I don't know, potential energy like before and after, sort of that. Is that what it is?
Yeah, so before you would have relatively higher energy, they would have whatever their ground state energy is. And in the bonded state, they would have lowered their potential energy through that up-down interaction. What my brain was giving me as an image for this when I was reviewing it last night, if you're hanging off the side of a cliff, probably not a very big cliff, because why would you put yourself in that situation, but you're hanging off a cliff like in a movie, you've got both your hands on the cliff, and somebody comes over and they try to save you and they're going to pick you up. There's basically 2 ways that they can pick you up. It's going to involve 2 hands most of the time. There's the one where you basically, grab the forearm, or you grab the hand, right? 2 hands coming together, and that's each of our hydrogens putting in 1 electron. They're each putting in 1 hand to grab each other. They get a nice firm grip and hopefully pull you up the cliff so you're not dangling off the cliff anymore. The other way that you can do it is if you've got a big person, really strong person, or they're just motivated by the plot, right? They just reach down with both their hands and they just pick the other person up. That person's providing both the hands, both the electrons. That's our coordinate covalent bond. So those are basically like the 2 ways that you can do a bond. Each person puts in 1 hand, and that's stabilizing. You've got a good grip. Or one person comes along and just pulls the other person up. And that's our coordinate covalent bond. So generally, for valence bond theory, we will be looking at pictures soon. The valence electrons of our atoms reside in quantum mechanical orbitals, S, P, D, F, and their various M sub L, PX, PY, PZ, etc. That's where our valence electrons live. Our chemical bond is going to result from the overlap of 2 half-filled orbitals most of the time. Each atom puts in 1 electron to form that bond, and they're spin paired up and down. And then the geometry of the overlapping orbitals determines the shape of the molecule. Determined by orbitals. So depending on which orbitals are involved, that changes the shape. In a lot of cases, it's very similar to our valence shell electron pair repulsion theory, the shapes that we were talking about earlier and last lecture. Okay, so if we look at an example molecule, we're looking here at H2S. We've got hydrogens here with their 1s orbitals. They only have the 1s orbitals. We also have a sulfur atom. The sulfur atom has a bunch of orbitals, and we're looking at our orbital diagrams for our two hydrogens and for our sulfur. And so we can get this pairing, these sort of handshakes between our sulfur and our hydrogen. And that forms these bonds. We've got overlap between our p orbitals, and our p orbitals are angled, basically the three axes, p or px, py, pz. So they're all 90 degrees from each other. Our hydrogens just have their 1s, and so they're just bonding with the p orbitals. But based on where we've got extra space, we predict that it's going to be the 3p orbitals interacting with the 1s orbitals. So based on valence bond theory, we're predicting 90 degrees because p orbitals are at 90 degrees from each other. So that's why we're predicting this 90-degree bond angle. Valence shell electron pair repulsion theory predicts less than 109.5. We would have a tetrahedral electron geometry. That's the one where we hit the X and we turn 90 degrees at the torso, right? And then we get rid of two of those, and so we end up with the bent geometry. We would only be able to predict less than 109.5 degrees. The actual bond angle, according to people who've measured it, 92 degrees. So in this way, valence bond theory is closer than valence shell electron pair repulsion theory or Weisshaupt theory. All right, thinking about what is a chemical bond, it depends on the bonding model. According to valence bond theory, that's the one that we've just been talking about. What causes or what forms a chemical bond? Is it a lone electron pair? Is it an overlap between half-filled atomic orbitals? Is it an overlap between filled atomic orbitals? Or is it a shared electron pair between two atoms? What do we think? It is B. Valence bond theory says that it's the overlap between half-filled atomic orbitals. So that's like between the 1s and this was our sulfur. This would be 3s, these would be our 3p. So the interactions between those two electrons, those two hands that they're putting in, that's what forms the bond. However, this doesn't always work. And so here we're looking at an example where that doesn't work. The overlap of half-filled standard atomic orbitals, so our s and p and d orbitals, just as we've seen them in orbital diagrams before, this doesn't work for a lot of molecules. As an example, for carbon and hydrogen, we predict a formula of CH2 because our carbon has this for its orbital diagram. We've got two unpaired electrons. Only two unpaired electrons, and so it looks like we could only bond with two hydrogens. And so we would be predicting a similar structure to our H2S, but with carbon instead. So we'd have two hydrogens that can come in and interact with these p orbitals. But it actually looks more like this CH4 on the right. It does form a tetrahedral molecular geometry. It does form 4 bonds. So we need another concept to be able to explain why this is the case. And that concept is hybridization. So the orbitals in a molecule are not necessarily the same as the orbitals in the atom. So remember, molecule, we're bonding together, the atom is just the thing by itself. So our carbon before, when it's just by itself, right, this is its orbital diagram. When it gets into a bonding situation, things change. We get hybridization. So hybridization is a mathematical procedure where we combine our standard atomic orbitals. Basically, I'm not going to write that there. The atomic orbitals blend together. Blend or mix together. So rather than having separate distinct sets of s and p orbitals, we get a mishmash. They all combine together. They're still going to be localized, so they're still set on just that atom. They're not expanding outside of the atom, but they have different shapes and energies than our standard orbitals. Our standard orbitals being those s, p, d, and f. The shapes, fortunately, are things that we've already learned. They're shapes that we've looked at for electron geometries, so that's very convenient. We'll see some of those. So the point of hybrid orbitals is to minimize energy, lower our energy for our molecule by maximizing the orbital overlap. So blending, hybridization allows better overlap of our orbitals. We're slightly changing the shape, we're modifying the shape so that it fits the situation. And this often results in having directional lobes. So we'll have basically all of our electron density pointing out from the atom in one direction. Mostly points in one direction, as opposed to if we have a nucleus and we've got a p orbital, it's evenly distributed so that we've got probability, in this case, up and down. It's roughly evenly distributed, or it should be evenly distributed. In a hybrid situation, that would be very lopsided. So we would have this bonding side and then this other side that's not going to really be able to interact. We're kind of throwing all of our probability density out in one direction to get better overlap. If we think of the bonding as like holding hands, grabbing hands, this is like instead of just a standard like handshake, very nice, polite, prim and proper, this is the grabbing the forearm grip that you see big buff men do in videos, movies was what I was looking for. This is sort of that grip. You're getting, and then there's like a big slapping sound effect. I don't know why I'm talking about this so much. Okay, hybridization does require energy though. It takes energy to blend our orbitals together, and so there has to be some incentive. There has to be an energy payout. So if the energy that we get out from bond formation is big enough, then we can go ahead with this hybridization. It takes energy to rearrange our orbitals. We are going to just focus on hybridization of interior atoms, usually just one interior atom, and our terminal atoms are going to stay unhybridized. They're just going to be normal standard atomic orbitals. All right, some general statements about hybridization. The number of standard orbitals, s, p, d, f, with commas in there, always equal the number of hybrid orbitals with whatever their label is. So if we have an s and 2p in, how many orbitals is that? Total. What's 1 plus 2? 3. So we'd get 3 hybrid orbitals out. And they would all be the same because we blended them together. So if you put in 3 orbitals, you get out 3 orbitals. If you put in 5 orbitals, you get out 5 orbitals. If you put in 6 orbitals, you get out 6 orbitals. We're not changing the number of orbitals. It's always going to be the same. The way that we combine our standard orbitals determines our shape and energy of our hybrid orbitals. This is where the electron geometry names come in handy. So all of our electron geometry shapes come in handy here. And the way that we do the hybridization is going to go for lowest overall energy. Molecules want to be stable, they want to be low energy, and we're just going to use our electron geometries to predict the hybridization. It's not always going to be accurate, but it should be good enough for us. Questions so far? Okay, let's look at hybridization. So going back to our CH4 example, carbon bonding with hydrogen. Before we do hybridization, we've got our 2s orbital that's filled because we're past the s column, right? We're past the s block, we're in the p block, we're the second spot in the p block, so our 2p, we've got 2 electrons there. It looks like we've got 2 unpaired electrons. That would let us form 2 bonds with our valence bond theory. However, if we hybridize it, we blend all of these together, we blend our s and 3 of our p orbitals together, we get 4 sp3. So s and all 3 p orbitals blended together. Our labels for our hybrid orbitals is always just the labels of the orbitals that we put in. So sp3, it's always going to be in order too. So it's always s first, then we'll add in p's, and we can even add in a couple of d's. So our sp3 hybrid orbital, we know that we've got 4 because we put in 1 s orbital, we put in 3 p orbitals. And when we hybridize them, they all take on the same energy level. We've blended them together, they're nice and smooth and even. And so the 4 hybrid orbitals are degenerate. What does degenerate mean in this context? Does it mean they're good for nothing, low down, dirty dogs? The scum of the earth, filth? No. Degenerate in this case means that they have the same energy. So anytime you hybridize orbitals, the hybrid orbitals always have the same energy. That's why we're blending them together, basically. And if we look at the shape, on the left we're looking at our unhybridized atomic orbitals. These are the ones that we've seen before. So we've got our s orbital, it's round. We've got our px, py, pz orbitals. The dumbbells, or the single dumbbells, the peanut shape. And when they hybridization, they form the like bowling pin looking shape that I was showing you, that I drew for you previously. Each of these has a big lobe and the small lobe, if you look at them independently. If you look at them as a whole, we kind of just draw in the big lobes. And notice that we've got 4 orbitals, 4 hybrid orbitals. What's our shape for 4 electron groups? Tetrahedral. And this is tetrahedral shape. With each of our lobes pointing out in one of those 4 directions. Generally, we're just going to look at them. Usually, you would look at them all together rather than looking at them broken out separately. But it's also nice to see them that way. Okay, so for this sp3 hybridization, we've got a new orbital diagram because we hybridized our orbitals. And so we're going to have 4 half-filled orbitals. They have to have parallel spin because of Hund's rule. They fill in parallel singly first, and then we can double them up afterwards. And because we've got 4 half-filled orbitals, we can form 4 bonds. So if we've got hydrogens, right, 4 hydrogens, they can come along and they can pair these half-filled orbitals. Let's make a big mess of this whole thing. So that's how we're able to get 4 bonds out of our carbon. Get those overlap between our 1s of our hydrogens. Those are not hybridized. Overlapping with our hybrid orbitals. Questions about sp3? Okay, hybrid orbitals can also accommodate a lone pair. So if we've got a lone pair, that's going to reduce our tendency to hybridize. Ammonia contains sp3 hybrid orbitals. We've got our lone pair up there. The reason that it forms only 3 bonds, nitrogen has 5 valence electrons. If we draw out the sp3 orbital diagram, we have to fill in 5 spots. The first 4 go in up, the last one goes in down. So we've got a lone pair, and then we've got 3 of those sp3 orbitals that are available to bond. So again, our theme is half-filled orbitals can overlap with other half-filled orbitals to form bonds. Except in the case of coordinate covalent bonds, which we don't really talk about very much. That mostly happens with like metals, like transition metals can do coordinate covalent bonds. All right, how many sp3 hybrid orbitals result from the hybridization of 1s and 3 p orbitals? Briefly discuss with your neighbor. Okay, discussion time is over. How many orbitals do we get out? 4. Why 4? For every orbital in, we get 1 orbital out. So we put in 4 orbitals into our hybridization machine, and poof, pops out 4 hybrid orbitals. So the number in equals the number out. So we have 4 sp3 hybrid orbitals. It will always be 4 sp3 hybrid orbitals every single time. And it's always going to have that tetrahedral shape. We can also have sp2 hybridization. So one of our p orbitals not participating in the hybridization process. So when we undergo the hybridization, we go from our standard atomic orbitals to our sp2 hybrid orbitals. We've got 3 of them because we put in 3 orbitals, and we've got 1 unhybridized p orbital. So we've just got a regular p orbital left over, not participating in the hybridization process. So that's a normal p orbital. And so what our hybridization looks like, we've put in 3 orbitals. We get out 3 orbitals. All right, we put in an s and 2 of our p orbitals. And our geometry for 3 electron groups, trigonal planar. So it's flat. It's that YMCA, the Y in YMCA pose. Trigonal planar. So we can bond with each of these hybridized lobes. The reason that we're hybridizing is so that we can bond. So those are each going to form bonds. Or they'll be occupied by a lone pair. So H2CO has sp2 hybrid orbitals. Normally, hydrogen, oxygen, carbon. Carbon would have 2 unpaired bonds. It goes through hybridization. So we're taking this, we're putting it through our hybridization machine. We've got 3 bonding opportunities because we've got these half-filled orbitals. So each of those can go on to bond. Some of them will go and bond with the hydrogens, and then that third one can go on and bond with the oxygen. And this p orbital can also bond with oxygen. So let's see what that looks like. That looks like this. So we've got our carbon. Yeah, that's probably the best color. Carbon. Here it's got its sp3 hybrid orbitals. So it's that flat trigonal planar geometry. We've got some bonds with hydrogens. Those are single bonds. We've also got one of those bonding with the oxygen. So our carbon hybrid orbital bonds with oxygen 2p orbital. That's this bond in the middle. And then we've got this hot mess of above and below. And that's from our unhybridized p orbital from our carbon. So that would be sticking straight up and down to minimize the overlap with our hybrid orbitals. So it's sticking up and down. And then oxygen is also going to have a p orbital that's in that direction, because it's got 3 p orbitals. The other one would be in and out of the board relative to the way that we're looking at it. The one that's shown here is up and down. And so these can have side-to-side overlap, which is not nearly as good as direct overlap. And I don't have a good hand-grabbing analogy for this. If anything, it's like people reaching over a fence to pass a hot dog because they're doing a barbecue. I don't know. Okay, so breaking that down. We've got 2 types of bonds. We saw some symbols there. We've got a pi bond, pi, like the Greek letter. or magnum. So our pi bond, pi symbol, the same one that we use in math, the little table. That's resulting from p orbitals overlapping side by side. Do that in a color that's not red. So our pi bond is this weird shape. And the electrons occupy both lobes. Because why wouldn't they? Usually we just show the electrons being on one side, but they are actually in both, which is a little bit weird to me. And then we also have sigma bonds. That's our lowercase sigma sign. The capital sigma sign is, I think, this one that looks like an E. Right? That's also sigma, but we're looking at lowercase sigma. So our sigma bonds are end-to-end overlap. That's our handshake overlap. So our half-filled px orbitals that we're showing here can overlap directly on one of their lobes. In the case of our H2CO, it's a hybrid orbital from carbon and a p orbital from oxygen that are overlapping end to end. That direct overlap is better than this kind of sideways overlap. It's a better hold. Questions about that? Cool. So the way that we label these bonds is with the type of bond. So they're sigma, they're end-to-end direct overlap, or they're pi bonds, they're sideways, they're parallel overlap, pi for parallel maybe. So we signify the type of bond, sigma or pi, as well as the type of overlapping orbitals. So for our CO sigma bond, the sigma is the direct overlap bond. It's our sp2 from our carbon, and it's the p orbital from our oxygen. Just one of our atomic p orbitals. We don't have to specify which one. Our carbon also has that unhybridized p orbital that's overlapping with the p orbital, also unhybridized, of our oxygen. So sigma is straight on, direct overlap, pi bonds, parallel overlap, side to side. One advantage that valence bond theory has over Lewis theory is that it does give us some explanation for the different types of bonds. So valence bond theory predicts that the double bond contains two different kinds of bonds. So we've got a sigma bond and we have a pi bond. We've got the end-to-end, we've got the side-to-side. Our pi bonds, because they're that parallel overlap, they're kind of that reaching over the fence overlap, they're not going to be able to overlap as well. They kind of have to both stretch to get that orbital overlap, and that's not as good as that direct end-to-end sigma overlap. So that pi bond is generally going to be easier to break than a sigma bond. So pi bonds are generally weaker than sigma bonds. So that's our sigma, and that's the pi. My very bad artist's interpretation of them. This also does a couple other things for us. Because we know that we've got two different types of bonds. One of them's an end-to-end bond, and the other one's that parallel bond. Those end-to-end bonds, because they're overlapping symmetrically, you can have rotation around a single bond. You can twist one or both of these groups, and they're still going to have that overlap because we're rotating around the axis where the overlap is. When we get to double bonds though, right, we've got these up and down configurations. If you try to rotate those, you lose your overlap. You would have to break the bond in order for those to not overlap anymore. So the pi bond would break because you lose overlap. So things that have double bonds can't rotate. Things that have single bonds can rotate. So in this 1,2-dichloroethane molecule that we have here, these chlorines are stuck on the same side. They can't rotate to be on the opposite side. In our dichloroethane, these chlorines could move to any of the other spots because we've got free 360-degree rotation around the bond. And this is just what I was talking about. I didn't put on Do Not Disturb, and now I have it on. Great. So free rotation around single bonds. Single bonds can rotate. This also kind of breaks the handshake analogy because you can't rotate 360 degrees in a handshake. But whatever. When we've got the double bond, these are two distinct and separate chemicals. If you tried to order like some version of 1,2-dichloroethane, that's the single bonds only version, these are going to be exactly the same. There's no way that you could just buy this one on the left. The cis 1,2-dichloroethane, cis being they're on the same side, versus trans where they're on the opposite side, you can buy these as separate chemicals. You would probably you might pay a little bit more versus getting a blend, but I don't really know because I'm not a synthetic bench chemist. But these will not readily interconvert. You would have to put in enough energy to break the double bond to reform in the other version. They will not interconvert. Okay, wall of text. Previously, we learned that double bonds are stronger and shorter than single bonds. Makes sense? A carbon-carbon single bond has an average bond energy of 347 kilojoules per mole. If you double that, it would be something like 700. It would be 694 kilojoules per mole. The carbon-carbon double bond has an average bond energy of 611 kilojoules per mole. That is not double, right? That's less than double. So why is a double bond not just twice as strong as a single bond? Discuss with your neighbor. Okay, why is our double bond not just twice as strong as our single bond? What are our two types of bonds? Our two Greek letters of bonds? Pi and sigma. Yeah, pi and sigma bonds. If you have a single bond, which one of those bonds is that? Is that a sigma bond or a pi bond? That direct overlap, that's going to be the sigma bond. So we've got good direct overlap of our orbitals. If you add another bond on top of that to add a double bond, to make it a double bond instead of a single bond, how's our overlap then? What kind of bond are we forming? That's going to be the pi bond. That's our sideways overlap, and that's not as good an overlap. And so it's weaker than our other type. And so the reason that it's weaker than just double the strength is because we've got the sigma, that's the end-to-end overlap. Sigma's formed, you could also think of it as between s orbitals, and pi bonds form between p orbitals, p for pi. We can also have sp hybridization. If we do sp hybridization, we're blending one s and one p atomic orbital. So we get two sp hybrid orbitals, two in, two out. And we're left with two unhybridized p orbitals. So two just regular px, py, pz, whatever they are, orbitals. So that might look something like this. They're going to get a linear geometry. Our electron geometry, when we've got two groups, is linear. So we're using those valence shell electron pair repulsion theories, those Vsepar theory names, but all the ones just with like no lone pairs. So our two groups, we've got two hybridized orbitals, so we get linear geometry, the lobes sticking out in opposite directions. So if we do acetylene, which basically just has this Lewis structure, acetylene is going to have sp hybrid orbitals. Our carbons are going to have hybrid orbitals. So we're putting an s orbital and a p orbital into our hybridization machine. We've got our hybrid orbitals that are sticking out. I don't like the way that I drew that. Hybrid orbital is sticking out in a linear geometry, and we also have p orbitals that don't overlap with those. Even though one of them looks like it does, I'm just bad at drawing in 3 dimensions. If we look at the number of unpaired electrons, we've got 4 unpaired or 4 half-filled orbitals. That means that we can form 4 bonds. It's half-filled orbitals that bond. So if we look at acetylene, HCCH, we've got our carbons in the middle. They're bonded to hydrogens on either side. They use their hybrid orbitals to bond with the hydrogen and also to bond with the carbon. That's how they get their sigma bonds, the end-to-end overlap. They also each have P to P pi bonds that can form. So we've got the end-to-end overlap, and then we've got p orbitals that are in the up-down position and p orbitals that are in the coming out of the board going into the board position. And so we can get sideways overlap between both of those orbitals, and they're half-filled. So we can form 2 pi bonds. Questions or confusions about that? Would anyone like to guess if we can rotate around this bond? Can we get rotation? No, definitely not, right? Because we've got the pi bonds and their sideways overlap. If we twist them, they're going to break that overlap. They're going to lose their overlap. That's not going to fly. So that would result in breaking both of our pi bonds. It's definitely not going to happen. So that's our third of our relatively simpler cases. Thinking about CO2, as one does, what is the hybridization in CO2 for our central atom. You may need to start with a Lewis structure. If we do a Lewis structure, we're going to have carbon in the middle, oxygen on either side, and we'll have double bonds. We'll also have lone pairs on our oxygens. Those are less important. So we've got 2 double bonds. What sort of bonds, what sort of things go into a double bond? A pi and a sigma. So for this we need 1 sigma and 1 pi. For this we need 1 sigma and 1 pi. So how many half-filled orbitals do we have to fill out these 4 bonds? Alternatively, we can just think about like what's the shape of CO2. How many electron groups do we have on carbon? 2. 2 electron groups, so we're going to have a linear shape. Linear shape is going to go along with sp. So carbon in the middle needs to reach out with some sp hybridized orbitals. The oxygens on the outside can reach out with a p orbital. And then we've got an up-down interaction. P and P. And we've got an in-out interaction with the other one. So pi, pi. Drawing in 3D is so fun. So one of the other ways we can figure out this sp is we have to have 2 pi bonds. Means we need 2 unhybridized p orbitals on carbon. So the maximum hybrid orbitals that we can have is 2 sp. Sorry if the explanation isn't good. It's been so long since I've learned it. But that's it. You're bonding with 2 things, it's sp. And we don't have any lone pairs. We can also have, what I was alluding to previously, expanded octets. So elements in the 3rd row, starting in the 3rd row and no higher than that, starting in the 3rd row and below, we can have expanded octets. Why can we have expanded octets? Does anyone remember? Yes, they have the d orbitals. So they've got those extra unfilled pockets, those d orbitals that we can put electrons into. And so we can also tap into those for hybridization. So our expanded octets are going to result from, or be related to, hybridization of d orbitals. Our 3d orbitals are similar in energy to our s and p. They get closer spacing the higher n number that you get to. So adding in our row of 3d orbitals, we can blend our s and our p's and one of our d's. So how many orbitals are we putting in? 5. Right, s plus our 3 p's plus our 1d, total of 5 orbitals. 5 orbitals in, 5 orbitals out. So we get 5 sp3d hybrid orbitals. And this gives us the trigonal bipyramidal arrangement. So we've got the axial in the up and down positions, and we've got 3 in the equatorial positions going around the sides. And that would be something like this arsenic fluoride structure. So we've got 5 bonds. We need to form 5 bonds. We need to hybridize 5 orbitals. So we put in an S, 3 Ps, and a D in that order. And we get lobes that are half filled in each of our directions, each of our trigonal bipyramidal directions. Otherwise, for arsenic, we might get it's going to be, those would be our atomic orbitals, right? So it looks like we can form only 3 bonds, but if we hybridize those, blend them together, and throw in a d orbital just to make the extra space, then we can get 5 bonds. So that's how we're able to get 5 bonds that form, and our bonds are all sigma bonds because they're single bonds. So we've got sp3d overlapping with one of the p orbitals from our fluorines, because that's where fluorine has its one unfilled electron, or one unfilled orbital. Okay. We can also have sp3d2 hybrid orbitals. So we're putting in 1 plus 3 plus 2, 6 orbitals in. We get 6 orbitals out. And 6 groups is going to give us octahedral geometry. So for example, something like sulfur hexafluoride. Our sulfur has undergone this hybridization process. So it end up with sulfur would have 6 hybrid orbitals that are each half filled. So those can each go on to bond. Fluorine is taking its one half filled p orbital and contributing that to the bond. And since it's a single bond, it's a sigma bond. Sigma is single, pi is double. Parallel. Questions? Okay, if we want to write hybridization and bonding schemes, the rigorous way to do it would be to do calculations. Like throw it in a supercomputer and have it do all the calculations, or just probably a regular computer at this point. And it would be able to do a decent enough job. But for us, it's good enough to just assign a hybridization scheme based on the electron geometry. So we find the electron geometry from a Lewis structure, and then we ask ourselves, how many different electron groups do we have? How many hybrid orbitals would we need to get that shape? So find the electron geometry, the number of electron groups will be the same as the number of hybrid orbitals. The reason that it's important that we do the electron geometry is because if we have lone pairs, we're not going to necessarily see those just based on the atoms that are present. The cases that we've been looking at, it's matched up that our electron geometry has been the same as our molecular geometry. That's not always going to be the case. So sometimes we'll also have to have an empty hybrid orbital or a full hybrid orbital that's just an electron pair, a lone pair. And here's a table that has all of those shapes in it. And it's just our electron geometry shapes. So if you've got 2 electron groups, it's linear, it's sp. Because you've got 2 groups, so you need 2 hybrid orbitals. You start from s, you count up through p, and then you tap into d if you need it, and you can use it. If you've got 3 electron groups, you need sp2, because you have 1 s and 2 p. Which is a total of 3, and so on and so forth, counting down the line. So our first step, we want a Lewis structure. So we have to be able to do a Lewis structure. We can use our valence shell electron pair repulsion theory to predict electron geometry around the interior atom based on number of electron groups. Then you fit the correct hybridization based on those number of electron groups. And then you can sketch the molecule if necessary. And we can label with sigma or pi notation, as well as the type of overlapping orbitals. Let's see what this looks like. Okay, hybridization and bonding scheme for xenon tetrafluoride. We need to do a Lewis structure. Xenon has 8 electrons. Fluorine, we've got 4 of them. They have 7 electrons each. So that's going to be 28 plus 8. We've got 36 electrons. Xenon is going to go in the center. Fluorine only likes to form 1 bond. So we put our xenon in the center. Fluorine's around the outside. To get everything connected, we need 4 bonds. So our minimum bonding electrons is 8. We're going to be left with 28 remaining electrons. What is the goal in Lewis structures? How do we know when we're done giving electrons to an atom? Yeah, when it has a full valence shell, when it has a full octet. So looking at our fluorines, they've each got 2 electrons from the lone pair. We can give them 6 more. And 6 times 4 is 24, so we're placing 24 electrons there. Which means we've got 4 electrons left. Everything has a full octet. Where can we place our 4 electrons? We give them to the xenon. We can give them to the xenon because xenon is big. Xenon has access to d orbitals. It has access to expanded octets. So we're going to give those as lone pairs. I don't know why I wrote that the way that I did, but that would be our Lewis structure. How many electron groups do we have on our xenon? Yes, it's 6. So our electron geometry is what? Is octahedral. To get the octahedral shape with hybridization, we would need to have 6 hybrid orbitals. So xenon is going to have sp3. How many orbitals is that so far? 4. We need 2 more, so we're going to tap into our d orbitals. We're going to pick up 2 of those. So it's going to be sp3d2 hybridization. We're putting in 6 atomic orbitals, we're getting out 6 hybrid orbitals. And they're going to have the octahedral shape. So we'll have 1 going up, 1 going down, and then 4 in the equatorial positions. And that's how we're going to get all of these bonds filled out. So we are going to have basically the shape that we see here. Let me do this in a different color. I'm going to use filled wedges to indicate that they're coming out of the board, and unfilled ones to signify that they're going into the board. And then we've got a lone pair up and a lone pair down. So this should be a square planar geometry so that our lone pairs are as far away from each other as they can be. And if we do a look at one of these bonds, because they're all going to be the same, we're going to get a sigma bond between our xenon, it's the sp3d2 hybridized orbital, and the fluorine with the p orbital. Questions about any of those parts or details? Cool. You could also do a hybridization and bonding scheme for HCN, but we're out of time, so maybe we'll do that next week.